When asked to find absolute extrema of a function, you will be given a function and a closed interval restricting how many x values you can use. You may follow these steps, and I hope they're helpful. Take the first derivative and solve for x to identify critical numbers. Substitute your critical numbers that lie inside the given interval and the interval endpoints into the original function. Your largest answer is the absolute maximum value, while your smallest answer is the absolute minimum value. Example, give the absolute maximum and minimum of the function, and we're going to start with the function f of x equals x cubed minus 3x, only on the interval from 0 to 3. Over here on the graph, uh, the orange portion from 0, and I didn't plan very well, to 3. There's way more to the graph than that, but we're only asked to focus on 0 to 3. Let's jump in there and get our critical numbers. First derivative is 3x squared minus 3. Factor out of 3. Break this up as a difference of two squares. We can ignore that lead 3 because it doesn't have a variable. But x squared minus 1 will factor as x plus 1 times x minus 1. The first factor gives us a critical number of negative 1. The second factor gives us a critical number of positive 1. Now, this negative 1, even though it's a critical number, negative 1 does not fall inside the interval from 0 to 3. It's just too small. Positive 1 does fall inside the interval. So when we get ready to look for our maximum minimum, we're going to look at 0, 3, and only the critical number 1. This critical number, negative 1, is legitimate, but it's just not inside that interval. Going to the original function, x cubed minus 3x, substitute the interval endpoints of 0 and 3, and also the critical number that fell in between. In the original function, if we sub in 0, our answer is 0. Paired up, 0, 0 is this point at the top right of your screen on the graph. The interval endpoint of 3 subbed into the original function produces an answer of 18, which by chance is our largest answer. That's our absolute max. The critical number inside the interval 1 plugged into the original function gives us an answer of negative 2. And since that's our smallest answer, that's our absolute minimum. Now, what do these points tell us? On the graph, from 0 to 3, negative 1 produces our smallest answer, our minimum value, and 3 produced our largest answer, or the absolute max. But again, we're restricted on what x values we can use. Give the absolute maximum and minimum of this function. And for this one, we have x squared minus 4x minus 3. Our interval is from 0 to 5. So even though this graph has a never-ending stretch from left to right, we're only going to concentrate on this orange portion from 0 to 5. Nowhere else. Let's get our critical number. The first derivative is 2x minus 4, and that's equal to 0 when x equals 2. Then make the decision, is 2 inside of this interval? It is. So we're going to use that and our interval endpoints. We're going to calculate f of 0, f of 5, and f of 2. F of 0 gives us an answer of negative 3, so the point 0, negative 3 will be on our graph, and that's this left endpoint. The right endpoint of 5 gives us an answer of 2, so the point 5, 2 is going to be at the other end of our graph in the intervals that we're supposed to stay within. And then since 2 is a critical number, it will mark a hilltop or valley floor. We can tell from the graph it's going to mark a valley floor. 2 plugged into the original function gives us an answer of negative 7. So 2 is our absolute max. -7 is our absolute minimum. And you can tell by the graph that's the lowest and highest point in the interval for that function. Let's begin a new topic called concavity. Concavity is the curvature of a function. If a graph is concave up, then it's curved upward. If a graph is concave down, then that means it's curved downward. To find intervals of concavity, we're going to use the second derivative. If the second derivative is positive, the graph's curved upward. If the second derivative is negative, the graph is curved downward. The point where concavity changes is called an inflection point. Let's investigate this function below. Discuss the concavity of the function and find the inflection point if it exists. An inflection point will exist if your concavity changes. So if you go from concave up to concave down, the point where that changes is called your inflection point. All right, so now with concavity, you need to take two derivatives. The first derivative is rate of change, and that one's good for increasing or decreasing. The second derivative is where you check concavity. So our original function, let's take the first derivative, that's -3x squared plus 18x. The derivative of this derivative is -6x plus 18. It's the second derivative we use to check concavity. So the critical number of our second derivative is 3. This is an inflection point if concavity changes. Now, just like we did in previous videos, for the second derivative, we take our critical number, mark it on a number line, and we're going to test left and right of it. And that's what you see here. I've marked 3 on this number line. Pick a number smaller than 3, larger than 3, and test them both in the second derivative, because that's the one that checks for concavity up or down. The second derivative with 0 plugged in is positive, so that tells us the graph is concave up or curved upward. The other test number, 5, plugged into the second derivative gives us a -12, and that's concave down. Once you get past 3, this other interval is curved downward. Curved downward. Concave up, left of the critical number, that's this lavender section. Concave up from -infinity to 3. Concave down in this light pink section, and that's 3 to infinity. That's the section after the critical number. Now, since concavity changed at the critical number, the inflection point, and this is the original graph, so you use the original function. Plug your critical number into the original function, that's -3 cubed plus 9 times 3 squared minus 47. Use your calculator, you'll get 47. So that tells us at the point 347, the concavity of this graph changes. It goes from being curved upward to curved downward. Discuss the concavity of this next function. We have the function -2x cubed minus 9x squared plus 1. The graph is down here towards the bottom right of your screen. The first two derivatives, we get -6x squared minus 18x, and then another derivative takes us to -12x minus 18. The critical number for this second derivative, we add 18, divide by -12, reduce, and that's -3/2. On the graph, when x is -3/2, I'm going to mark that with this red dot. Draw a number line, mark your critical number on it, and then test numbers on either side of it. So down here, bottom right of your screen, I've marked -3/2. Pick a number smaller, pick a number larger as your test numbers. Remember, if you're asked to test for concavity, use the second derivative. So this test number of -3 plugged into the second derivative gives us a positive answer, so that tells us concave up. The other test number, 0, substituted into the second derivative, gives us a negative answer, and that just tells us our graph is curved down or concave down. If you look at the graph on the right side of your screen in the middle, you will see that our math and our picture match up. Our graph is curved upward until you get to the critical number, and then it's bent or curved downward afterwards. There is a change in concavity, and that just means there's an inflection point. At the top right of your screen, concave up, -infinity till you get to your critical number, concave down from your critical number to positive infinity, and then since concavity changed at the inflection point, if you sub in -3/2 into the original function, you will get your inflection point. Type all that into your calculator, convert to a fraction, you get -25/2. And so that's the coordinates, -3/2, -25/2. That's the coordinates of your inflection point. Okay, let's look at an application of concavity. Consider the following function where R is the revenue in thousands of dollars and X is the advertising cost in thousands of dollars. So this function R, what it does is it predicts the money coming in thousands of dollars depending on X dollars spent on advertising. I went ahead and provided the graph of this function to the right. You don't ever have to have the graph of these, but it sure helps if you're a visual learner. Now we're asked to focus only on the interval from 0 to 5, which means the revenue if we don't spend any money advertising, all the way up to the revenue if we spend $5,000 in advertising. Let's take our first two derivatives. Here's our original function. Our first derivative is -3/2 x squared plus 6x. And then the derivative of that gives us our second derivative, -3x plus 6. The critical number of the second derivative is x equals 2, because -3 times 2 plus 6 is 0. We know that based on the way the graph looks, 2 is pretty reasonable. That looks like the part where the graph goes from being curved upward to curved downward. In green, I've only highlighted the 0 to 5 interval because we were asked to stay between 0 and 5 with our x values. So that's what I did by highlighting this portion of the graph in green. Okay, so after we've got our first two derivatives and we've got the critical number of the second one, the point of diminishing returns is the point where you can keep spending more money on advertising, but the rate of revenue starts to slow down. It doesn't mean your revenue goes down. It just means that spending any more doesn't result in a giant or a greater increase in revenue. It's almost to the point where the juice isn't worth the squeeze. I know that's kind of a weird analogy, but let's go with it. We've got the critical number of 2. That's going to be your first number. The point of diminishing returns, you go to the original function to plug that critical number in. So R of 2, this is the revenue of spending $2,000 in advertising. Substitute that in, use your calculator, you get 15. So the point of diminishing returns for this problem is the point 215, which if you're asked to translate that is 2,000 spent on advertising leads to a $15,000 revenue. Let's go back up and look at the graph. This point of inflection, this point of diminishing returns, see, the revenue actually peaks over here around 4. 1, 2, 3, 4. Yeah. Around 4 is where you actually reach maximum revenue. But notice how the rate increases rapidly. And then once you hit this critical number of 2, you're still increasing in revenue, but it's not as fast. So, long story short, if you're asked to find a point of diminishing returns, it's the inflection point. I hope this video helps. Reach out by phone or email if we have class together. For sure, ask in class.